Welcome to the second part of the lecture. In this video, I'm going to go over the sketch of the proofs of theorem 1 and theorem 2. First, let's look at theorem 1, for which the dimension is equal to 3. First, we are going to show in the hyperbolic case, the entropy is equal to 2. And there are a few essential steps. First, we're going to use the method by King and Marquich. They prove that the cardinality of the set SMG epsilon is bounded from above by a multiple times g to the power 2g. G denotes the genus. And on the other hand, there's a subset capital G mg epsilon, whose cardinality is also bounded from below by a constant numbers, constant times g to the power 2g. And here, let me briefly mention the definition of this subset capital G. They constructed an essential minimal surface by attaching some pair of pans. And this, in particular, this surface is sufficiently equidistributed in L. Okay, now we take this subset G to be the elements whose like containing the finite covers of the minimal surface. So for all the candidates, they are all well distributed in M. And this property is very useful in the proof of the rigidity part. We're gonna see that later. Okay, and back to this proof. The second step is that we use the uniqueness theorem. We use the estimate of second fundamental groove due to Seppi. He proved that we take a surface subgroup in S epsilon capital M, and we let S be the area minimizing guy in the homotopy class of pi. Okay, then the theorem says that the principal curvatures on S goes to 0 as epsilon goes to 0. And now we can also deduce this formula, the area of S. We have that because like we can start with the sectional curvature restricted to S01 to 1. This can be computed by the integral of the Gaussian curvature K plus 1/2 of the square norm of the second fundamental form on S. Okay, and we also know that by Gauss-Bonnet, the integral of Gaussian curvature is equal to like 4 pi parentheses 1 minus g, then plus the integral of a squared over 2. That's it. Then we just need to add 1 in the integrand, and we put some terms to the other side, and eventually we have, like we are going to have this formula. Okay, because we are looking at the hyperbolic case, so the second sectional curvature is always equal to -1. Therefore, this part, -1 plus 1 vanishes. Okay, and from Seppi result, we also know that the second fundamental term is going to 0. So that is to say, when epsilon is a very small number, the area of S in the hyperbolic metric is comparable to 4 pi g minus 1. It's very close to this number. Okay, and that's also to say that the number of minimal surfaces that is bounded by 4 pi j minus 1 is comparable to the cardinality of our side as mj epsilon. Okay, and so we can just replace this part in the definition of minimal surface entropy by the cardinality of S, and we have the formula. We know that the cardinality of S is bounded both from below and above by the similar terms. So we can say that the entropy must be 2. Okay, so we finished the proof of the hyperbolic case. Now let's move on to the second case. Suppose we have another Riemann metric H on M, and it has sectional curvature less than or equal to 1. Then we can say the entropy must be greater than or equal to 2. Moreover, the equality holds if and only if H is isometric to H0, the hyperbolic metric. And to prove that, I only want to mention the K lemma in the proof, because the theorem follows directly from this lemma. We take a sequence of surface subgroups in capital G, Mg I1 over I. So for each pi I, it has limit set a 1 over I, 1 plus 1 over I quasi-circle. And let Si be the error minimizing surface with respect to H0. On the other hand, we let sigma I be the error minimizing surface with respect to H. Okay, then we can show the length soup as equals to infinity of the quotient, the error of H with respect to H of sigma I divided by the error with respect to H0 of Si must be less than or equal to 1. Also, the equality holds if and only if H is isometric to H0. And we are only going to look at the proof of this K lemma. And we have seen that the error of sigma I can be represented by this formula. By assumption, we assume R1 to 1 is less than or equal to 1. So this part is negative, less than or equal to 0. And this part is also less than or equal to 0. So clearly, the error must be at most 4 pi g minus 1. And on the other hand, if we look at the error of this denominator, it's approaching 4 pi g minus 1 when I goes to infinity due to Zappe's result. So the inequality part is clear. Okay, now for the rigidity part, when the equality of star holds, then as a direct result, we have this. Okay, the limit of this average integral is equal to 0. Okay, but we also want to have that the total integral equal to 0, because if we have that result, we can consider the limit of the surfaces, and in the limit, both parts are equal to 0. So we are able to say the sectional curvature is equal to -1. It is hyperbolic, and it has 0 second fundamental form. So that's also totally geodesic. That's ideal. And so we want to have, we will look at the universal covers of the surfaces. So we want to prove that there exists a sequence of disks omega I in the 3-ball with respect to H, which is lifted by each sigma I, such that the limit of the integral on omega I is equal to 0. Okay, when we have this result, we can take the limit of omega I. It converges to another disk, omega. And for omega, it has, because omega I has boundary 1 plus 1 over I quasi-circle. So for the limit omega I, its boundary must be a round circle C. Okay, and so omega must be totally geodesic from this this equality, and it has sectional curvature equal to 1, -1. And not only that, we also want to have the projection of omega to be dense in M, because we want to show the metric H on the whole manifold is hyperbolic. Okay, and to show that, we need a little preparation. We introduce these notations. First, let the set C be the collection of all round circles in the boundary sphere. And from here, we take a subset L of C, which contains the elements such that there exists omega I, which is lifted by sigma I, such that the boundary of omega I converges to C. So it contains round circles, which is a limit, which is the limit of a sequence of boundaries of omega I. Okay, now next we are going to show there is an element, a round circle in L, such that it has dense gamma orbit in C. And why we need this? That's because like if this is true, we can apply a result by Gromov. They said that there's a map from MH0 to MH that takes geodesics to geodesics. So it also takes total geodesic, like if we consider the universal cover. The same map also takes the total geodesic disk to the totally geodesic disk. So there is, we have this totally geodesic disk bounded by round circle C that maps to omega. Okay, and consider the projection in M. If we have this result, then the projection of D of C must be dense in M. So under the map, the projection of omega is also dense. And it is totally geodesic, and it is also hyperbolic. Now we just need to like apply the frame flow that is ergodic. So we are able to extend the result on to the whole manifold. We can show that the whole manifold has sectional curvature equal to -1. That is hyperbolic. That's roughly the proof. So it left to prove that there's such an element in L. Okay, and to say that the K-lemma is due to Ratner and Shar, they said that the closure of projections of a total geodesic disk in H3 to M is either equal to the whole manifold M, or it is a closed geodesic surface in M. And if the first one is true, then we're done. So now we assume by contradiction that this never happens. So we assume L has no dense element. That is to say, any projection must be for any projection of the total geodesic guy that is equal to a closed total geodesic surface in M. Okay, and then in the paper of Pellegrin, Marquez, and Nevis, they are able to show that these elements are must be isolated. So because of that, that's also like finite. And that's actually contradicts the equidistribution property, because when the surface is equidistributed, we can show that for any compact subset in H3. We can always find an element C in L such that it determines a total geodesic disk D of C asymptotic to C, and that intersects the set K. This is non-empty. And from here, we claim that all the element C such that D of C intersects the fundamental domain of M the set of all these elements must be an infinite set. That is because if this is only finite, like we can take out all this element, we can take out all these intersections from the fundamental domain, and we can always take a subset in the remaining part. However, there's no intersection with the remaining part, so it contradicts with this claim. Okay, and that's why the lemma is true. Then, just as I said previously, we have this density result, and we apply the ergodicity of the frame flow, and then we can show the metric H on M must be hyperbolic. Then due to most rigidity, that must be isometric to H naught. Okay, that's roughly the proof for dimension 3. Now, in my theorem, when the dimension is higher, I want to talk about the difference in the proof. Firstly, we also want to see the minimal surface entropy of hyperbolic metric is equal to 2. That's independent of the dimension. And we have this similar result. The cardinality of S is also bounded from above by this by this quantity. And of course, C2 depends on the dimension. And on the other hand, there's also a subset capital G, which is bounded from below by C1G to the power 2G. Here, the construction of capital G is due to Hammerstedt. In her paper, she proved that she constructed an essential surface that is well distributed. And she also proved that by attaching in some pairs of planes. And but the result is only true when N is odd. That's why we put this in our assumption. Roughly speaking, when you, in order to obtain a pair of planes, we need to glue some polygons up together, and in that part, we need to assume the flip condition. That is to say, in each connected component of identity of the center of the Lie group, there must be a reflection as an inner automorphism. And that excludes the case for even dimensions. And that's why we need this. Okay, and apart from that, we still have some issues like in Shen Yao's existence result, when the dimension is greater than equal to 4, the error minimized surface might have some branch points. So we don't have this result in this case, because when there exists some branch points, the second fundamental form blow up. And to deal with that, we are going to consider the error minimizer mod 2, and I'm going to explain this. First, we take a sequence of surface subgroups in SMGI 1 over I, and we let SI be the error minimizer in each homotopy class. And let's leave that for a while. On the other hand, we take the I to be the error minimizing surface mod 2 in HN. That is asymptotic to the same boundary as the lift of SI. So we can look at this picture. They have the same boundary. This picture is a little weird because I'm not able to draw the picture for hierarchical dimensions. So we just imagine these curves means the minimal surfaces, and the boundary must be a quasi-circle. And there's a result by Almgren that the error minimizer mode 2 has no branch points. So DI looks good. And from here, we can show that DI converges smoothly on compact size to another minimal surface mode 2, which is called D. And also their boundary converges to a round circle. Okay, then from this compactness result, the round circle, because we are looking at the hyperbolic case, the round circle only bounds a unique minimal disk, and that is also totally geodesic, whose second fundamental form is equal to 0. So we have this result. The norm-squared second fundamental form on DI converges to 0. Okay, so we show the results on DI. It left to show that DI is identical to SI triple, the lift of SI. And we're gonna say that from a uniqueness lemma. In general, suppose we have a minimal surface D in HN, and if the norm squared second fundamental form is bounded from above by 2, then this surface D must be the unique minimal surface with a fixed asymptotic boundary. And I'll quickly go over the sketch of the proof. Like in this picture, suppose we have this surface D, and we are going to look at the equidistant hypersurface to D. Like we can take this hypersurface called HR, meaning that it has a fixed distance R to D. And we can compute all the principal curvatures on HR. So it's not hard to show that the hyperbolic space minus D is foliated by the sequence of HR. for all the positive numbers R. And by computing the principal curvatures on HR, we can say that this is too convex, meaning that the sum of any two principal curvatures is positive. So suppose there's another minimal surface asymptotic to the same boundary. It has mean curvature equal to 0, so it cannot be tangential to any of this HR. Therefore, any other minimal surface must be identical to D. That's why it is unique. Okay, so we have finished this part, and repeating the same procedure, we can compute the minimal surface entropy. Okay, now for second part of the proof, when there's another metric with sectional curvature less than or equal to 1, the inequality part is the same, but we still have some trouble in the rigidity part. Like in the previous case, we used the theorem by Ratner and Shar. They show that the closure projection of the total geodesic disk to M is either equal to the whole manifold or equal to a total geodesic surface. However, in this case, it can be a finite union of total geodesic proper submanifolds. So it's like, suppose we have, for example, let's assume the dimension n is equal to 5. So the projection can be either a geodesic surface, whose dimension is 2, or a geodesic 3 submanifold, or a geodesic submanifold of dimension 4. So unlike the 3-dimensional case, if we assume there's no dense element in L, we no longer have this property. It doesn't have to be isolated because, like if we consider the elements, they can be accumulated at some lower dimensional spheres. Okay, so also we don't have the unique, the finiteness result. And we have to look for some other result to prove that. And to deal with that, I applied the theorem by Moses, Shar, and also by Li and Ao. They both prove that for any infinite sequence of proper geodesic submanifold, it either becomes dense in the whole manifold M, or it has a subsequence content in a higher dimensional proper geodesic submanifold. For example, let's look at the case when n is equal to 5. Let's suppose the first case never happens. Then we will find the contradiction. Here we need a little more notation. We let P be the set of proper total geodesic submanifold. That is the closure of projection of some totally geodesic disk DC, where C is an element in L. And as a direct result, P must be infinite, just because otherwise, if that is finite, like we can take out all the element from M, and there's another subset in the remaining part, and it has no intersection with all the elements of the total geodesic disk, and that contradicts with the equidistribution. Okay, so P is infinite, and in this case, n is equal to 5. So the codimension of each submanifold can be from 1 to 3 because that the dimension is from 2 to 4. Okay, we let P sub k to be the subset of P, which contains submanifold of codimension k. Okay, that's all the notations. And we claim that all the elements in P are contained in a union of finitely many proper submanifold. And if that is true, we can also take a set from the remaining part and find the contradiction with equidistribution. Okay, so it suffices to prove this claim. First, let's consider P1 when the codimension is equal to 1. If P1 is infinite, then we just need to apply this theorem. We take this infinite sequence. It must be dense in M because the codimension is already 1. So weird. We have this contradiction. Okay, now second case, if P1 is finite and P2 is infinite, then we take an infinite sequence in P2 from the theorem that must be contained in a submanifold of codimension 1. And by taking a few steps, it's not hard to show that this limit P is contained in P1. It's also a projection of some totally geodesic disk. And okay, and we take take out this sequence from P2, and we consider all the remaining elements in P2. Like we can continue to take a further subsequence, and that corresponds to another element in P1, and we keep going until like the remaining elements in P2 is finite. And we must stop infinite steps because P1 has only finitely many candidates. So eventually we show that the union of P1 and P2 is containing a finitely many, finite union of submanifold. Okay, now the last case. If P1, P2 are both finite and P3 is infinite. Similarly, we can consider the infinite sequence in P3. But in this case, we should be more careful that we take the sequence such that it is contained in P1 of maximal codimension M1. And the purpose for doing that is that like when we due to this maximality, like there's no intermediate submanifold between the sequence and P1. So applying this theorem, the sequence cannot be contained in any intermediate submanifold. So it must be dense in P1. Okay. So we have this, we conclude this. The sequence becomes dense in P1. And then we are able to show P1 is in the site P sub M1. And we can just keep going. We take out this sequence and choose another sequence in the remaining set of P3, and each time we want the sequence to be contained in a manifold of maximum codimension. And repeating this for finite steps, eventually the remaining elements in P3 must be finite. So we take the sum of P1, P2, P3 that must be contained in finitely many proper submanifolds. So we're done. We prove that. We prove the claim, and that contradicts the equidistribution. So the rigidity result holds. Okay, so that's all about the proof. And finally, I also want to mention a few further questions. You can think about this if you are interested in this topic. Firstly, we only prove the result when the dimension is odd. So like it's natural to consider what if it has even dimensions. Okay, and secondly, when dimension n is equal to 3, it was proved by law and Navis that when the scalar curvature of H is greater than or equal to -6, then the corresponding entropy is less than or equal to 2. And we also want to extend this result for higher codimensions. So we are also curious about the case where n is greater than 3. And of course, in this case, the scalar curvature must be greater than or equal to -n minus 1. And so we want to know if we have a similar result. And the last question, when the dimension is n is equal to 3 or higher, it's also conjectured by Calgary, Marcus, and Navis that there's an inequality related to the minimum surface entropy and the volume. Here it says the product of E of H and the volume with respect to H to the power 2 over n is greater than or equal to the product related to the hyperbolic case. But we still have no idea how to prove that. So we can continue to consider these further questions. Okay, that's all about my talk. Thanks for watching this video.